This is the first in a series of resources on integral calculus. We define the idea of an integral. We investigate the fundamental theorem of calculus and look at some basic rules for integrals. We explain the difference between definite and indefinite integrals, looking at a basic example. We consider using Riemann sums as a method for approximating a definite integral. We investigate the integrals for specific function forms, including polynomials and trigonometric functions. We will also look at substitution methods to simplify certain integrals. In the series of resources on derivatives, we realize that the velocity is the derivative of the location function for an object. More generally, we define the derivative as the instantaneous rate of change for a function. We also discovered how to find these derivatives for various function forms. But can we go the other direction? If we know the function that defines the derivative, can we find the original function? That is, can we find the antiderivative of a function? Consider a situation where we drive a car at a constant speed of 60 miles per hour. How far have we traveled in 2 hours? But this is just a simple distance problem. To find the distance, we simply multiply the rate by the time. So we have 60 multiplied by 2, and we find that we have traveled a distance of 120 miles. How will this help us with finding antiderivatives? Well, what happens if we think about this problem graphically? Let's think about the function graphed when we have time on the horizontal axis and the velocity on the vertical axis. Because we are driving at a set speed, the graph of our velocity function is the horizontal line at y equals 60. Since we are worried about the distance traveled in 2 hours, we consider the x values from 0 through 2. Finding the total distance traveled is exactly the same as finding the area of the rectangle shown. So in graphical terms, the antiderivative is the area between the graph of the function and the x-axis. What happens if we do not maintain a constant speed? For example, suppose our object starts from rest and accelerates at a constant rate. It reaches its target speed of 50 meters per second after accelerating for 5 seconds. How far did the object travel while getting up to full speed? Intuitively, we are trying to find a distance traveled. Because we accelerate at a constant rate, we can use our average rate and find the distance we travel at that speed for the elapsed time. Since we are starting from rest, the starting velocity was 0. We averaged the starting and final velocities to find our average velocity of 25 meters per second. Multiplying by the elapsed time of 5 seconds, we find the object traveled 125 meters while getting up to full speed. But how would this work if we consider the problem graphically? Dividing the final speed by the time elapsed, the velocity is 10 meters per second. This works since the object accelerates at a constant rate. We graph this velocity function, which is the linear function shown. To find the distance traveled in getting up to speed, we want to find the area between the function and the x-axis. Since this area is a triangle, our formula is 1/2 multiplied by the base multiplied by the height. The base is the elapsed time of 5 seconds. The height is the final velocity of 50 meters per second. Plugging in, we have 1/2 times 5 times 50, which equals 125 meters. We are now ready to formally define the antiderivative. We have the integral from the lower limit a to the upper limit b of some function f of x with respect to x. Graphically, this finds the area between the graph of the function and the x-axis, as we saw in the examples explored earlier. In future resources in this series, we will discover methods to calculate these integrals, as well as ways to simplify the problems.